So for today's question, we have Emily asked, what is the difference between RT-PCR and PCR in terms of things like monitoring gene editing? What are the benefits of using one over the other? How is RT-PCR more beneficial than regular PCR? Um, so the key difference between PCR and RT-PCR is just what you start off with. So PCR, which I have highlighted here, your starting initial thing is going to be DNA. Or it's going to be DNA. And RT stands for real time or reverse transcriptase. That's what the R and T stand for. And PCR, well, it's just the same. It stands for polymerase chain reaction. And the idea of PCR is just to amplify or make it very obvious of the gene that you have. So, just make some space. So that's the key difference. They're both essentially going to look at the amplification of a specific gene. It's just one is going to start with RNA and one is going to start with DNA. And so RT is the one going to start with RNA. And there's a big molecular mechanism on how this works. Essentially, if you have your mature RNA, this M stands for mature, not to be confused with messenger, okay? It's mature RNA. And you're going to add some primers in this. So we can call this P, primer P. And then reverse transcriptase, which is this enzyme, is going to go in here and convert it to cDNA. So if you notice, we went from RNA to DNA using this reverse transcriptase enzyme. And the C here stands for complementary DNA. It's the complement to the RNA, because if you remember, RNA is going to use U base pair instead of, or and opposed to DNA. DNA is not going to use the U. Anyways, so let's make some space again. In regards to monitoring gene editing, if you're editing genes, it's most likely that you're going to be using the CRISPR-Cas9 system, CRISPR-Cas9 construct or Cas9 system. And typically, actually, you're not going to use PCR or RT-PCR to monitor the gene editing to prove if it's valid or not. Usually, you'll use some sequencing models, so it can be like Sanger sequencing, or you can use XCal when you put your CRISPR vector into a bacteria. And so the way XCal works is you'll have this is your vector, and this will be the gene called LAC, I believe it's called LAC-Z. And when you insert a vector here, LAC-Z on its own will produce a blue color. But when you insert your gene for gene editing, it'll break up the XCal, and the colonies will end up coming white. So you'll see white colonies, and that's how you know that you successfully inserted it. If this is for a very specific class where they want you to use PCR or RT-PCR to monitor gene editing, then this method might not work, but typically in the lab space, that's what you would use to make sure that your CRISPR gene editing is working efficiently. And now in terms of better, RT-PCR could be better depending on what you're looking for. So assuming that you have a virus and inside is just single-stranded RNA, you can run PCR on this because PCR, its initial starting point uses DNA. So if you had a virus that only has single-stranded or double-stranded RNA, then you could use RT-PCR, because if you remember RT-PCR, its initial starting point is using RNA, which will turn to cDNA, and then you go through regular PCR, and that'll help you be able to it'll be able to help you amplify the genes inside this virus that only has DNA. So I hope that answers your question.